Welcome to Study Loop.
So we're given that neutrons are placed in a magnetic field that has a magnitude of 2.3 Tesla. And we're asked what the difference in energy between the states with the nuclear spin aligned field are. So we know that the magnitude of the energy of each of these states is given by either plus or minus mu of the neutron times b, the strength of the magnetic field. And now we think, because the neutron will tend to align with the magnetic field, meaning that's the preferred orientation, this must correspond to the state with the lower energy. So this tells us that aligned, the energy state must be minus mu nb. And conversely, the anti-aligned state must correspond to the positive value. The energy difference between these two states is simply the difference between the two, which is just twice mu naught b, or mu sub nb rather. And this comes out to be a value of 2.22 times 10 to the minus 26 joules. Next, we're asked to find the frequency and wavelength that is absorbed or emitted by a photon. So a photon would mediate the transition between the spin-aligned state and the spin-anti-aligned state, or vice versa. We know, it's a little messy, we know that the transition in energy between the two states is given by twice mu sub nb. And we know that this must also be equal to the energy of the photon, which is given by hf, where f is the frequency of the photon. So solving for f now, we have that this must be equal to 2 mu n b over Planck's constant. And plugging in values, we end up with 6.7 times 10 to the 7 hertz. Now using the simple relationship that lambda is c, the speed of light, over f, we find that the wavelength of such a photon must be given by plugging in numbers again, 4.48 meters. And those are our answers.